Good morning, ma'am. I'm Tejaswini from CSO. For my today's seminar, the topics of Unit 1 I'm going to talk about are coherency, interference and its types, superposition principle, thin films and the derivation of the cosine law, and Newton rings. So the first topic is coherency. So what is coherency? Two wave sources are said to be coherent if their frequency and waveforms are identical. That is, for two waves from different sources to be coherent, they must have same frequency, same wavelength, and a constant phase difference. Let's consider an example. Let's take a sine wave. Now let's take another wave. As you can see, these two are clearly not coherent because they have completely different waveforms. Now let's take another example. Now let's take another sine wave. But even though these waveforms are same, their wavelengths are clearly different, thus frequency is also different. These two can also be not considered as coherent. Now let's take another example. As you can see clearly, up to this point, these two waves are coherent, but after this, clearly their phase difference changed. That is not a constant phase difference, thus these two waves are also not coherent. Now, let's take another example. Let's take a cos wave for the sine wave. Now, as we can see clearly, these two are coherent because even though they may look different, they have same frequency, same waveform, that is, same wavelength, and a constant phase difference. That is, their phase difference is not changing at all. It always remains pi by 2. Thus, this is a definition of coherency. Also, coherence is an ideal property of waves that enables stationary interference. That is, for interference to occur, coherency is a must. Now, coming to the second topic, interference in itself. What is interference? Stating in simple terms, interference is the combined effect of disturbance caused by each individual wave at same place and at the same time. Now let's take a sine wave, another sine wave. These two may look different, but both are sine waves and they have same wavelength, frequency, and phase difference that is 0, as you can see, but different amplitudes. There is different wave characteristics. So what is the interference phenomenon here? Interference is nothing but disturbance caused by the combining of two waveforms when they come close to each other. So, because of these two waveforms undergo interference, these will result a completely new waveform formed from these two. Let's understand interference more clearly through a visual representation of Young's double slit experiment. As we know that in Young's double slit experiment, there are straight wave fronts are passed through two slits. Because of those two separate wave fronts, they are from different sources are formed and undergo interference. Let's see a visual representation to understand this. As you can see clearly, from two places, two wave fronts are getting passed. Please wait a minute. Yeah, as you can see, two waves are getting passed, and here they are undergoing a phenomenon which is nothing but interference, where they are going to result of a new waveform formed from these two. Now, interference can be understood with more clarity from a principle called principle of superposition. What is it? When two or more waves travel through the same medium simultaneously, the resultant displacement at any point is the vector sum of the displacement due to the individual waves. As we have seen before, to put it more clearly, we're taking two waves but with different wave characteristics, even though they have same wavelength, same frequency, and a constant phase difference. Let's see this clearly with the visual representation. Let's see this experiment. Two wavefronts are formed here due to the dropping of nail into the water causing ripples. These ripples are nothing but waves. So one ripple of wave y characteristic y1 and other is y2. So the result will be r equals to y1 plus y2 after superposition. This is a good demonstration of superposition in our daily life examples. that is rippling of water. See, like this. Their wave characteristic is changed because their amplitudes are adding up, giving a waveform of more amplitude compared to the before two. So now moving on, let's talk about what are the different types of interference. As we discussed before, interference is nothing but disturbance caused by combining of two waves. So how this disturbance is called? One is there are two types of interferences. One is constructive interference and second is destructive interference. What is constructive interference? Let's see a visual demonstration to understand clearly. As you can see in the below image, two waveforms but with a phase difference of 0 or can be stated as n multiples of pi, that is there is no change, no difference, no phase difference at all. And these two wave forms we have taken have similar wave characteristics, that is y1 and y2 are almost similar, resulting a waveform with greater wave characteristics, say, that is amplitude of y1 plus y2. In this case we can say as 2y, that is its wave characteristics like amplitude are doubled. So this is called constructive interference, and in this constructive interference case we obtain maximum displacement, that is maximum amplitude. Also we have to note that always in constructive interference the phase difference is always in the multiples of pi, that is n pi, and the wavelength is considered as n lambda. Now, what is destructive interference? What happens in destructive interference is, let's consider a point on one waveform y1 and other point on other waveform y2. What happens is, at these 2 points, suppose in first waveform it is positive, then the corresponding point in its counterpart waves, that is the second wave, is considered as negative regardless of its magnitude. That is, one is positive, another is negative. So on combining these two waves, clearly uh, in the resulting waveform, the wave characteristics will be less compared to the two parent waveforms, because due to the opposite signs of their magnitudes, the negative waveform and positive waveform part of the waveform gets cancelled, resulting a waveform with much less wave characteristic, say amplitude, compared to the before two. So what we have to note in destructive interference is, in destructive interference, as you can see clearly, the phase difference is in the multiples of pi by 2, because of which this phenomenon occurs. That is, the phase difference in destructive interference is in the multiples of pi by 2, that is 2n minus 1 into pi by 2, and its wavelength will always be in the form of 2n minus 1 into lambda by 2. And also, clearly, destructive interference is the case in which the resulting waveform will have least displacement, that is least magnitude, compared to the two waveforms from which it is obtained. So, that is all about coherency, uh, interference, and its types, and superposition principle. Now, let's continue our discussion on thin films experiment. So this is the main diagram of thin film experiment, in which, as in the diagram, the thin film PQRS is taken of thickness T. So what happens in this experiment? Now, on the top surface of the thin film, that is PQ, a light ray AB is instanted as shown, and from there it takes two parts. Some part of the light or of the instant light is reflected back to the air medium itself, that is the reflected ray PC, and some other part of the light ray gets refracted, and this is the uh, refracted ray PD. And on reaching the bottom surface of this thin film, this ray gets refracted once again to once again reach top surface PQ, that is, this is another refracted ray DE, and from the point E, the light ray goes out into the air medium once again, that is, this is emergent ray EF. So what's this phenomenon here? Here we have from one incident light ray, that is from one input, two outputs, that is one reflected light ray which is directly reflected after the immediate incidence, and the emergent light ray which comes out of the thin film after going through refraction. So we can clearly see that these two waves, two light rays of their own particular waveforms are close to each other, the phenomenon of interference occurs between those two light rays. So let's see how it occurs clearly through a representation, visual representation that is. As we can see clearly, uh, two rays are formed, that is incident ray and reflected ray and the emergent ray, and these two have their own waveforms, and these two waveforms, since are close to each other, either forms destructive interference or a constructive interference. So the result of this is what causes the different colors on the soap bubble we generally see in our daily lives. That is, based on the different angle of incidence, the phenomenon of interference occurs differently between these two um, waveforms. That is, for different angle, the phenomenon of interference occurs differently, resulting a different waveform of different intensity at each time. So since it has different intensity, of course, it will have different wave characteristics, thus different color, which is why we see different colors from of Vibgyor on the soap bubble in our daily lives. Let's see clearly through an image. As you can see in this soap bubble, we can see different colors because as as per the perspective of our eye, the instant light from our eye when it strikes the soap bubble, what we discussed in the thin film experiment occurs, and the uh, emer emergent ray and the reflected ray, which we have seen in the previous experiment, undergoes interference, resulting a different uh, light ray of different waveform with different characteristics each time, giving different colors, which is what we can see in this beautiful image of this soap bubble. Not only this soap bubble, there are other daily life phenomenon we see of thin films. So these are some of the images of thin films in our real life. That is, during rainy season, we sometimes we see petrol dropping on the road or diesel dropping on the road, because of which we can see these different colors, because a thin film is formed by this layer of petrol or diesel. And not only that, we can see in for some insects, their wings are so transparent and so thin, they can act as thin films, and this phenomenon of interference occurs in them too, letting us seeing different beautiful colors from their wings, which is nothing but what we discussed earlier in this thin film experiment. Now, this what we have to find from this thin films experiment is the formula for path difference. So, what is path difference? As we know that path difference is nothing but path of light in second medium into refractive index of that medium, that is mu2, minus path of light in first medium into refractive index of the first medium. So what is path of light in second medium and path of light in first medium? Let's see from the diagram. As we can see clearly, path of light in second medium, that is, this is the path itself, right? What is it? BD plus DE, which is what we have written here too. That is, path of light in second medium is BD plus DE, and in first medium it is BC. That is, as we can clearly see that BC is the reflected ray, which is the path of light, original path of light in the first medium. That is why we are taking it as a path of light in first medium, that is BC. And clearly we know the second medium's factor index is mu2, first medium factor index is mu1. So now in order to find the path difference, we need to know the values of BD, DE, BC in considerable terms. So let's to find these values, we are going to consider three triangles from this diagram. That is triangle BHD. That is this triangle. Another triangle DHE. This triangle, and this triangle in the error medium, which we are drawn, BCE, which I have drawn as it is here. no alteration at all. Also, as you can see, this is r is nothing but angle of refraction, because this is angle of incidence, this is the angle of refraction, and by the rule of alternative angles, this angle and this angle are equal. Hence, this is angle of refraction 2. This is angle of refraction 2. So this is angle of refraction, and this is also angle of refraction, because these two will be equal since they are here. This refracting ray is actually reflecting from this bottom surface and is getting refracting back into the original medium. Thus, this is angle of refraction. This is also angle of refraction, that is which we have indicated by letter R. And as we can see clearly here, this is angle of incidence, because by the proportionality and its equality terms, this angle and this angle are clearly equal. So how we're going to use these terms in the experiment? So now consider the triangle BHT, since we have to find the value of BD, DE and BC. From this, to find BD, we have to find the value of cos R. Cos of, that is cos of angle of refraction. That is cos R is clearly, as you can see, adjacent side by hypotenuse, that is adjacent side is HD by hypotenuse BD. And as we can see from the diagram that this HD is nothing but the thickness of this thin film, so that is T. And from this we can clearly write that BD equals to T by cos R. And in the similar way, from the triangle HED2, that is this triangle also, we can find the other unknown in this path difference formula, that is DE, as D is equals to T by cos R, similar to how we found BD in the triangle BHT. We also get value of DE in triangle HED. To find the value of BE, let's consider triangle BHT once again and write tan R, tan of angle of refraction in it. What is tan R? Opposite side BH by adjacent side HD, that is BH by HD, that is BH by T, from which we can write BH equals to T tan R. Similarly, from triangle HED, we can write HE as T tan R too, because they are of course similar triangles. So now, in order to find the other unknown in this path difference formula, that is BC, we're gonna consider the triangle BCE, which were drawn in the rarer medium in our diagram. So let's and we also seen that this I is the angle of incidence due to the proportionality law. So sine I, in this, from this triangle we write sine I, which is sine I equals to opposite side by hypotenuse, right? So BC by BE, that is BC by BE. BE is nothing but, as we seen in the diagram, once again we'll see BE is nothing but BH plus HE, which were derived before in our equations 3 and 4. So in place of BE we'll write BH plus HE. So sin I equals to BC by 2T tan R. And from this we can write BC as 2T into tan R sin I. And for our convenience, we'll multiply a term and divide the term sin R for this expression, and we'll write tan R as sin R by cos R, and sin I by sin R, and other term sin R is left here. So we know that from Snell's law, refractive index equals to ratio of sin I to sin R, that is mu equals to sin R by sin R. So BC equals to, we can write it as, substituting the sin R by sin R with mu, BC equals to 2 mu t sine square R by cos R. Now let's take this equation as equation 5. Now substituting the values in the unknowns, that is in this path difference equation, that is BD, DE, BC, from the equations, equation 1 BD, equation 2 DE, and equation 5 BC, will substitute and we'll get the path difference equation like this. So solving this, 1 minus sine square r equals to cos square r, since sine square r plus cos square r equals to 1, we'll write this as this. These two gets cancelled and we'll get path difference formula as 2 mu t cos r. But depending on how much light is getting entered into the medium, because sometimes several irregularities exist. Maybe not the entire light may pass through the maybe utilized for reflection and refraction. So let's say uh, some part of the light is omitted. With this in mind, we can generalize this formula as, when not the entire light is getting reflected and some part of the light is due to some other irregularities it is not taking part in this experiment. We'll generalize this formula as path difference equal when not whole light is not getting involved in the experiment equals to 2 mu t cos r minus lambda by 2. This is the required formula for path difference in this experiment. Now let's see how it goes in the cases of constructor interference and destructor interference, which we discussed before. As we discussed before, for constructor interference, the path difference, that is sigma, is always in the n multiples of lambda. So we'll equalize this and we'll write in place of sigma in this equation as n lambda, and on solving it we get that 2 mu t cos r equals to lambda by 2 into 2n plus 1. We can use this formula when if it is given in the question for constructor interference to find mu, that is the refractive index of the thin film, or t, that is the thickness of the thin film, or that is the angle of refraction 2, or lambda, wavelength of the light. Similarly, for destructive interference, path difference is odd multiples of lambda by 2. So that is, we'll substitute this value, that is sigma equals 2n minus 1 into lambda by 2 in this formula once again and solve it, from which we get that 2 mu t cos r equals to n lambda. So by using these general formulas of constructor interference or destructor interference, or even the generalized formula, we can find various parameters or unknowns throughout this thin films experiment. So this is the completion of thin films experiment explanation. Now let's come to the last topic of this chapter, that is Newton's rings. Now this is the main diagram of Newton ring. So what are the apparatus required in this Newton's rings are a glass plate, a planar convex lens, a beam splitter, traveling microscope, and a source of light. This is the arrangement of this experiment. That is, we'll take a source and light is emitted from it, and this diverged light is converted into parallel beam of light using a convex lens, and this parallel beam of light will incident on the beam splitter. Here the beam splitter is placed at an angle of 45 degrees, as you can see here, and thus since the parallel beam of light is also incidenting at an angle of 45 degrees, it also reflects at an angle of 45 degrees, thus it goes straight down towards this planar convex lens, which is where we take the air film. And since this light rays, parallel beam of light rays are incidenting at normal with respect to this base of the planar convex lens, since these light rays are incidenting at normal, they get reflected back once again. Since they are incidenting at normal, they also get reflected back at normal too, resulting two waveforms here. That is, the incoming light rays after reflection from the beam splitter, and the outgoing light rays after the reflection from the base of the planar convex lens, and the phenomenon of interference, that is the superposition of incoming and outgoing light rays, takes place here, which pass through the beam splitter and reaches this traveling microscope, which collects this data, which in turn gives us what we call as Newton rings. That is, this Newton rings is nothing but the resulting waveform of the interference of these incoming and outgoing light rays with different wave characteristics gives us these different Newton rings. So now that we've seen what's happening in this experiment, let's see a visual representation of it to get more clarity. So let's see what happens. Light wave incidents a parallel beam, gets here, gets reflected back, interference occurs C in this air medium and corrected by the traveling microscope, and this output is nothing but these Newton's rings, which is nothing but the output of the interference of these two interfering incoming and outgoing waveforms collected here. So let's discuss about the theoretical part of this Newton's experiment. So in this too, we need to find an equation for path difference. So clearly from the thin film experiment before, we know the path difference equals to, for a thin film, that is here, our thin film is nothing but air film is between this planar convex lens and this glass plate. So we have this for this film, path difference is 2 nu t cos r. But in our experiment, we can clearly see that there is no refraction taking place. There are only reflections. So refraction angle is taken as 0 and clearly mu equals to 1 because in this time the thin film is in itself is an 8 film, thus its refractive index is 1. So substituting these two values of r and mu in this equation, we get sigma equals to 2 into 1 into t cos 0, that is sigma equals to 2t. We are adding lambda by 2 because due to interference and several other irregularities, we get a path difference and extra of lambda by 2. Thus, the generalized formula for path difference here is 2t plus lambda by 2. But even though we don't know the value of t here, unlike in the previous case, so we need to find value of t first. So, determination of thickness of air film. Now, let's consider a Newton ring in the result. Clearly, the outermost ring of the resulting Newton rings will be congruent in terms with this planar convex lens because because from this itself it is resulting, right? So let's take this ring which is congruent to this planar convex lens part. So let's talk about the radii in this circle. Now, the radius OA equals to Rn, which is nothing but radius of the Newton's ring. This Rn is also equal because these two are radii of the same diameter, so they are equal. That is the radius of the Newton ring. Now consider the vertical diameter. What's happening here? Here, this OD is T because this is a planar convex lens, and this is, as we discussed before, is the air film, which is T, that is the thickness of the air film. So that is T, and this remaining part OC will be CD minus OD, that is 2R minus T, where 2R is nothing but the diameter of this planar convex lens, that is R is the radius of the planar convex lens. So we'll write these terms here clearly. Now, from circle properties, we know that diameter is always same. That is horizontal diameter is equals to vertical diameter, and by Einstein's formula, OA into OB equals to OC into OD. That is for horizontal components, and these are vertical components. And substituting these values, we get Rn square equals to 2RT minus T square. Now here, we are going to neglect this T square because this is theoretical, right? Because T is thickness, right? What is T squared? There, such value do not exist in reality. So its values neglected because it's not possible practically, from which we get Rn square equals to 2RT. From this we can finally write the equation for T, that is thickness of this air film, which is equals to Rn square by 2R, where Rn equals to radius of the Newton's rings and capital R is equals to radius of the planar convex lens. Now substituting this T value in our path difference formula obtained for this experiment, which is equals to T plus lambda by 2, in place of T, we'll substitute this value to write 2 into R square by 2R in plus lambda by 2, from which we get the main formula for the path difference in this experiment, which is sigma equals to Rn square by capital R plus lambda by 2, or since radius equals to diameter by 2, where dn refers to the diameter of the Newton's rings, sigma can also be written as dn square by 4r plus lambda by 2. And like we seen before, we will also consider the cases of constructor interference and destructor interference. Here, sigma is and lambda, clearly we discussed before. Path difference of constructor interference is n multiples of lambda, and on substituting this value in the equation we obtain, we can get the diameter of the Newton ring, which is equal to root of 2r lambda into 2n minus 1. Now, For destructive interference, as we discussed before, it is path difference of destructive interference is nothing but odd multiples of lambda by 2. That is, we'll substitute this value in the equation we obtained for the path difference in this experiment, and on writing this, we'll get the equation for the diameter as root of 4r lambda into n minus 1. Here we're going to neglect minus 1 because we know that n is nothing but the number of images, that is the number of neutron rings formed. Since if the n is 1, 1 minus 1 has no meaning, that is, it's meaningless. Thus, we're gonna neglect that, which gives us a diameter as dn equals to root of 4 or lambda n. And from these derived equations of destructive interference or constructive interference, or the generalized formula here in itself, there's a path difference we obtained in this experiment. Using these, we can find the various parameters in the concerned experiment, that is, we can find Rn, that is the radius of the Newton rings given all other values, or the radius of the planar convex lens, or the wavelength of the light, that is lambda, or just the path difference in itself. So, in this way, in these both experiments of thin film and Newton ring, by using the formulas we obtain, we can find all other various parameters and unknowns we got to know in this experiment. So, so in this way, we covered all 5 topics of this chapter interference, that is coherency, interference, superposition principle, and the experiments, thin films, when we also derive the cosine law from it. That is the value of the path difference in this experiment and also in Newton's rings, and how we can use them in solving problems related to it. Thank you.